Hey folks, my name is Nathan Johnston, and in this video we're going to go through problem B1 of the 2024 Putnam. Okay, this problem, it's a bit of a mouthful, but it says let n and k be positive integers. Then the square in the ith row and jth column of an n by n grid contains the number I plus j minus k. And then what you want to do is you want to find for which values of n and k is it possible to select n squares from the grid, no two in the same row and column, such that the numbers contained in the selected squares are exactly 1, 2, 3, up to n. Okay, when trying to solve Putnam problems, I recommend starting off with small cases. Play around a little bit before you try to jump into just solving the entire thing. Get a feel for it, get some intuition. So that's what I'm going to do at the start of the video. I'm not going to jump right into a solution. The stuff that we do at the start is going to be useful for developing the solution, but think of this video more as a walkthrough. Okay, how would you come up with the solution rather than just, here's the solution, I pulled it out of a hat. Yay, we're done. Okay, so let's start off by playing around with small values of n and k and see if we can notice any patterns or any useful information that might help us develop a proof. Okay, so if we start off with n equals 1, what's this grid look like? Well, every entry in, like every square in the grid has the number I plus j minus k in it. So, I mean, this is just a 1 by 1 grid. It's just got the number 2 minus k in it. Yeah, that works, okay? If I choose k equals 1, then that single square there, it has the number 1 in it, and I can select that one square, and it satisfies all of the conditions of the question sort of trivially, okay? So let's move on to more interesting cases. What about n equals 2, for example? For n equals 2, what the square ends up looking like is, well, okay, we've got 2 minus k, and then 3 minus k in the top right and bottom left, and then 4 minus k in the bottom right. Okay, I've sort of made the convention here that I'm going to label the top left square as the 1, 1 square. Then as I move over, the column index increases, and I move down, the row index increases, just like we label entries in a matrix, basically. The top left is the 1, 1 entry, and then we move over in rows and columns from there. The bottom right is the NN entry. Okay, and when we do this, what's going to happen is every time we develop this square grid here, it's sort of going to be constant along anti-diagonals, going from the bottom left to the top right, because of this I plus j that's in the formula for its ij entry. Okay, anyway, so the question is, is there a choice of k that works in this situation? And remember, what works means is I have to be able to pick two entries that are not any of them in the same row or column as each other, such that I have 1 in one of those squares and 2 in the other square. And we can see very quickly that no choice of k works here, because if, for example, if I pick the top left and bottom right entries, okay, well, I've got the numbers 2 minus k and 4 minus k. There's no choice of k that makes those equal to 1 and 2, because those are always 2 separated from each other, not 1 separated from each other, right? And similarly, if I pick the bottom left and top right entries, those entries are always equal to each other. I always get like 1 and 1, or 2 and 2, or 3 and 3. I never get 1 and 2. I never get two numbers that are separated by 1 from each other. So for n equals 2, no, it never works. And maybe at this point I start making some mild general observations. For example, from here, like maybe I've got a little bit of intuition, I'm starting to get kind of comfortable with it, and I notice like at least there's a certain restriction on k that I can make, and that is, well, k's got to be between 1 and n, because otherwise I'm not going to have all of those numbers from 1 up to n appearing in the grid. If k is too small, if k is 0 or smaller, then the smallest number in the grid is 2. I don't have a 1 anywhere in that grid. On the other hand, if k is too large, if k is n plus 1 or larger, then I'm not going to have n appearing in the grid. Okay, so yeah, like k's got to be between 1 and n. All right, next up, let's go on to n equals 3. What do the grids look like? Okay, well, again, k's got to be between 1 and n, so there are only 3 possible grids that I might see here in this n equals 3 case. I've got the k equals 1 grid, k equals 2 grid, and k equals 3 grid. Do any of them work? For any of these, is it possible to select 3 squares in different rows and columns such that I get the entries 1, 2, and 3 appearing in those squares? Okay, and let's start off with k equals 1. Does this work? And let's just try to make it work. Okay, I've got to have 1, 2, and 3 in a square. So let's pick that one and only square that has the 1 in it. And very quickly I get stuck. Okay, if I pick that square that has the 1 in it, I have nothing left to pick. I cannot pick either of those two squares that have a 2 in it, because either it's in the same row as the 1 or it's in the same column as the 1. So no, there's no way to make that grid work. The k equals 1 grid, no, I'm stuck with it. It doesn't work. And for the k equals 3 grid, I have a similar problem because, well, there's only one 3 anywhere in that grid. And if I pick that 3, now I'm stuck. There's no way to pick a 2. The 2's, there are 2 of them, but they're all in the same rows or columns as the 3, so I'm not allowed to pick it. Okay, what about k equals 2? Okay, and well, it turns out k equals 2 does work. Okay, I can pick the 1 at the top middle, the 2 at the bottom left, and then the 3 at the sort of the rightmost center. And none of those are in the same row or column as each other. So yeah, this works. I can choose k equals 2. And at this point, I can make one more general observation. By the exact same logic that I used in the k equals 1 and k equals 3 cases, I can never choose k equals 1 or k equals n, no matter what n is, okay? If k equals 1, choosing 1 is always going to block the only two entries in that square. And if k is n, then choosing n is always going to block the only two n minus 1s in that square, okay? So there's never a way to make those work. Okay, so maybe at this point, I conjecture that maybe there's always a solution when k is between 2 and n minus 1 inclusive, okay? And I mean, this is kind of a thought process that went through my head when I was solving this problem originally. But then, like, there are mild gaps in this because, well, I mean, we already talked about n equals 1, and there is a solution when n equals 1. But it's kind of a trivial solution, so maybe that's an exception. I'm still going to roll with it a little bit. I want to go one step farther. I want to go on to n equals 4 and play around with that a little bit. I want to get a feel, like if my conjecture is true, then there should be a solution for k equals 2 and k equals 3. Okay, so I'm going to plop down those grids. Is there any way to pick, solutions in these cases? And let's start off with k equals 2. Okay, I have two choices for a 1. I'm just going to pick one of them randomly. I'll pick the one at the top. And now I only have one choice for the 2 that I can pick, right? Because I blocked the top and the middle 2. I must choose the bottom left 2. And now there's only one choice for the 3 that I can pick. And then once I choose that 1, 2, and 3, but now I'm stuck, okay? Each of the 4s is in the same row or column as either the 1, 2, or 3 that I picked, okay? And the exact same thing goes wrong if I pick the other 1 to start with. That was the only actual choice that I had anywhere. If I pick the left 1, well, I've got to pick the top right 2, and then I've got to pick one particular 3, and again, I'm going to get stuck. Okay, so for k equals 2, no, there's no way to do this. And the exact same thing goes wrong for k equals 3. If I just rotate this 180 degrees, I've got two choices for the 4, but then no matter which one I pick, I've only got one choice for the 3, and then one choice for the 2, and then no choices for the 1 to finish it off. Okay, so there's no solution in either of these cases. So I have no solutions at all when n equals 4. Okay, so my conjecture was wrong. Maybe at this point I flip around a little bit, okay? Rather than trying to find cases where there are solutions, can I find a more systematic way to rule out some solutions? I want to rule out values of n and k for which no solutions exist, okay? Now, this next step, this is the hardest one in the entire proof because this is where you've got to make a bit of a leap and you've got to do something really clever. This step here is what's going to separate the people who get 0, 1, 2, or 3 on the Putnam problem from those who get 7, 8, 9, or 10 on the Putnam problem. Okay, what we're going to do is, well, we've got these n squares that we're selecting in the grid. We're going to say, okay, well, if there is a solution, what sort of properties must that solution have? And one really simple to check property that those solutions must have is, well, okay, I mean, the numbers 1 up to n appear in those squares. If I add those up, I know what that adds up to. Okay, there's a nice formula for the sum of the first n numbers. But sort of more importantly, I can add it up in two different ways. Okay, I could just literally add up the labels 1 plus 2 plus 3 all the way up to plus n. Or remember way back when, early on at the start of the question, I was given a formula for those labels. I was told, well, in that box in the ith row, jth column, that's equal to I plus j minus k. So I could also add it up that way. And whenever you've got two different ways of computing something, that's really powerful. You can compute the two different things and set them equal to each other, and that gives you a condition that must be satisfied. So that's what we're going to do, okay? I'm going to add up all of the labels in the squares that I pick in two different ways, and that's going to give me a restriction on n and k. Okay, so let's do that. If I add up those labels, like I said, the labels are 1, 2, 3 up to n. Okay, so I just get the sum j equals 1 up to n of j. I'm just adding up the labels themselves. Okay, but that's got to be equal to if I, add up those labels where instead of just writing down, oh, the label is j, Okay, I'm going to write down the formula for the label. It's I plus j minus k. I'm adding all those up. And here I've got to be a little bit careful. Like, what am I summing over exactly? Well, I'm summing over all squares that I have selected. Okay, so let's just write that down. Okay, I'm not like summing I and j are both going from 1 to n or anything like that. I'm not summing every entry in every row and every column. I'm summing over pairs I and j where I've selected the square in the ith row and jth column. Okay, so that's what my sum is running over. Okay, and now let's try to evaluate the sum on the left and right-hand side here. Okay, on the left-hand side, I've just got the sum of the first n natural numbers. Very well-known formula. This is n times n plus 1 over 2. On the right-hand side, this is a little bit trickier. What I'm going to do is I'm going to break this up. I've got a sum of a sum, right? It's a sum of I plus j minus k. So that's a sum on the inside of the summation. I'm going to split it up into 3 individual sums, okay? So the sum of the i's plus the sum of the j's minus the sum of the k's. And I'm going to try to evaluate those sums individually. And this turns out to be doable, okay? This is not too bad. And the reason for that is, okay, the sum of the i's, for example. This means I'm summing up each row index of a selected square. But remember, those squares, every single one of them is in a different row. That's the condition here, right? Remember, I'm picking squares so that they're all in different rows and columns than each other. So this sum here, I'm summing over I see every single row index in that sum. So this is just a sum as, I goes from 1 to n. Okay, it's a sum in a different order. Like the i's here, they might be bouncing around, but it hits every number from 1 to n exactly once. So this sum here is also n times n plus 1 over 2. And then the exact same logic for the j sum. Remember, I'm summing over j, which is the column index, and well, I picked one square from every single column. So again, that sum, it has every number from 1 to n in some order in it. So that sum is also just n times n plus 1 over 2. And then the last sum, well, there are n terms in that sum, and each one of them is just equal to k. That sum's equal to n times k. Okay, and then I'm just going to simplify this down. I'm going to set that left-hand side equal to the right-hand side. I'm going to try to solve for n in terms of k or k in terms of n, whichever one ends up feeling more natural and which seems like it'll give me more useful information. Okay, so I do that on the left-hand side. Remember, I've got n times n plus 1 over 2. On the right-hand side, I've got, well, n times n plus 1 over 2 twice, so just n times n plus 1, and then minus that n times k. I'm going to rearrange and solve for k in terms of n, just because that works out a little bit cleaner here. And when I do that, I get k equals n plus 1 over 2. Okay, so in particular, that tells me a couple things. First off, it tells me n has to be odd. To have any solutions at all, n's got to be odd, because remember, k's got to be an integer. And the only way n plus 1 over 2 is going to be an integer is if n is odd. Okay, another thing that tells me is, well, for those odd values of n, there's at most one choice of k for which there's a solution, and this is it. It's this n plus 1 over 2. All other values of k, no, right away, no solution. Okay, it doesn't tell me that there is a solution for this value of k, though. This argument here, it only rules out values of k. So I'm not done yet. I've still got to show that when k is n plus 1 over 2, yeah, I've got a solution, okay? So let's clean this up, let's finish up that argument, and then we'll be done, okay? When k is n plus 1 over 2, is there a solution? And we've already done the small cases, right? When n and k are both 1, right? So n is 1, and then, okay, n plus 1 over 2, well, that's also 1. Okay, yeah, there's a solution. That's the n equals 1. That's the trivial case that we talked about way at the start of the video. The next one, if n is 3, the next odd number, okay, then 3 plus 1 over 2. Okay, so k is 2. Okay, is there a solution there? Well, yeah, again, that was the earliest non-trivial solution that we found. Okay, next up, let's just keep going, and then hopefully we can find a pattern in the solutions, and then we just write it down and say, oh yeah, there always is a solution. Okay, so we're hoping, for example, for the next value of n equals 5. Okay, then, well, n plus 1 over 2. Okay, so k is 3. We're hoping there's a solution, and we're hoping that there's sort of an easy to construct solution that has a nice pattern to it. Okay, well, here's what the square grid looks like in this case. And, well, okay, yeah, there is a solution. Fumble around a little bit, okay? What I'm going to do is, I don't know, maybe I'll pick the leftmost one, And then sort of what's the closest 2 that I can pick? Well, it blocks the 2s that are directly adjacent to it. I'm going to make sort of a knight move, like an L-shaped jump over to sort of the central 2. And then I just repeat this game. Okay, what's sort of the closest 3 to... I'll just jump in the exact same way over to the 3 in the top right corner, and I'll pick that 3. Okay, and now I've got to reset a little bit. Okay, what 4s do I have left that are not blocked? Well, there's only one 4 that's not blocked. It's at sort of the bottom left area, and then I can do an L-shaped jump over to a 5 from there. And hey, I picked 1, 2, 3, 4, and 5. They're all in different rows, all in different columns. This works. So there is a solution for n equals 5, k equals 3, and it looks something like this. There might be other solutions, but that's okay. I just need to find one. Okay, and maybe this grid here, this is large enough that I can start arguing generally about what a solution looks like in general. And I mean, sort of what's going on here is in the top half of this grid, I just picked like the left central one, and then I do these L-shaped jumps. So like I decrease my value of I, the row index, by 1, and I increase the value of j, my column index, by 2 every time. Okay, just write that down in formulas, okay? And sort of the way that works out is I'm saying that I'm selecting the squares where j is odd and I is n minus j over 2 plus 1. And that gets me the top 3 squares in this case, and in general, it gets me the top n plus 1 over 2 squares. Okay, so I've still got n minus 1 over 2 squares left. How do I pick those? Well, I just start in the very bottom row, second column, and do the same thing. Decrease I by 1, increase j by 2. Okay, and sort of what that looks like is now if j is even, I pick I equals n plus 1 minus j over 2, and that gets me the remaining numbers that I want to pick. Okay, and let's just double check that. Does that actually work in general? Okay, well, remember the labels on my squares, those are I plus j minus k, so let's just compute those labels, and let's hope that they really do end up equaling every number from 1 up to n. Okay, so we just write down the formulas that I just wrote down for I and j, simplify things down, and it turns out that then I plus j minus k is, well, if j is odd, then I get j plus 1 over 2 as the label in that square. And if j is even, I get j over 2 plus n minus 1 over 2 in that square, okay? And now let's think about what happens as j ranges from 1 to n. Well, as j is ranging over the odd numbers, that top quantity in like that sort of piecewise formula, that top quantity is ranging all over all numbers from 1 up to n plus 1 over 2, like I said, okay? It's ranging over sort of the first half values of n. Okay, and then in that second quantity, very conveniently, I've got this plus n plus 1 over 2 in it, so I just start right off at the next value. As j is ranging over the even values from 1 to n, this bottom quantity is ranging over, well, n plus 1 over 2 plus 1, all the way up to n, okay? So overall, yeah, this formula here, this label on the square, is ranging over all values from 1 to n, so I picked a square containing every number from 1 up to n in it, and I mean, that's it. Then I found a solution in these particular cases of n and k. So I've shown, yeah, all of those work. And then I'm done. So to sum up, our solution is that it's possible to select squares in this way exactly if n is odd and k is n plus 1 over 2. All right, and that's all I've got. Thanks for watching, everyone. I'll see you next time. We'll do another one of these videos, in a day or two.